Projectile motion. Objectives: projectile motion. Distinguish between a vector quantity and a scalar quantity. Explain how to find the resultant of two perpendicular vectors. Describe how the components of a vector affect each other. Describe the components of projectile motion. Describe the downward motion of a horizontally launched projectile. Describe how far below an imaginary straight line path a projectile falls. The big idea. Projectile motion can be described by the horizontal and vertical components of motion. In the previous chapter, we studied simple straight line motion, linear motion. We distinguished between motion with constant velocity, such as a bowling ball rolling horizontally, and accelerated motion, such as an object falling vertically under the influence of gravity. This little picture on the right is type 1 projectile motion. Now we extend these ideas to nonlinear motion, motion along a curved path. Throw a baseball and the path it follows is a curve. This curve is a combination of constant velocity, horizontal motion, and accelerated vertical motion. This is the second type. This is type 2 projectile motion. That's what the picture is, the graph picture on the right. And this is type 3 projectile motion. We'll see that the velocity of a thrown ball at any instant has two independent components of motion. What happens horizontally is not affected by what happens vertically. So there are three types of projectile motion we will study. Types 1, 2, and 3. How should you aim to hit a falling target? 1. On one corner of a rectangular piece of rigid cardboard, tape two 5-centimeter lengths of soda straws so they form a trough. Angle the straws to point towards the diagonal corner of the cardboard. 2. Draw a straight line passing through the center of the soda straws and extending to the top of the cardboard. 3. Tilt the cardboard so that marble 1 will roll downhill. Hold marble 1 in the upper right corner of the cardboard on the line you've drawn. Place a second marble in the trough formed by the two soda straws. Number 4. At the same time, release marble 1 and launch marble 2 by giving it a flick with your finger. 1. Observing. Did you hit marble 1? If so, what determined the point of collision? 2. Predicting. What would happen if you used marbles with different masses? 3. Making generalizations. Why do the two marbles fall the same vertical distance from the line in the same amount of time? 5.1. Vector and scalar quantities. It is often said that a picture is worth 1,000 words. Sometimes a picture explains a physics concept better than an equation does. Physicists love sketching doodles and equations to explain ideas. Their doodles often include arrows, where each arrow represents the magnitude and the direction of a certain quantity. The quantity might be the tension in a stretched rope, the compressive force in a squeezed spring, or the change in velocity of an airplane flying in the wind. A quantity that requires both magnitude and direction for a complete description is a vector quantity. Recall from chapter 4 that velocity differs from speed in that velocity includes direction in its description. Vector is magnitude and direction. Velocity is a vector quantity, as is acceleration. In later chapters, we'll see that other quantities, such as momentum, are also vector quantities. For now, we'll focus on the vector nature of velocity. Recall from chapter 2 that a quantity that is completely described by magnitude only is a scalar quantity. Scalars can be added, subtracted, multiplied, and divided like ordinary numbers. A vector quantity includes both magnitude and direction, but a scalar quantity includes only magnitude. When 3 kilograms of sand is added to 1 kilogram of cement, the resulting mixture has a mass of 4 kilograms. When 5 liters of water are poured from a pail that has 8 liters of water in it, the resulting volume is 3 liters. If a scheduled 60-minute trip has a 15-minute delay, the trip takes 75 minutes. In each of these cases, no direction is involved. We see that descriptions such as 10 kilograms north or 5 liters east or 15 minutes south have no meaning. How does a scalar quantity differ from a vector quantity? Air traffic controller, physics on the job. Busy airports have many aircraft landing and taking off every minute. Air traffic controllers are responsible for guiding pilots to their destinations. Using an understanding of vectors, air traffic controllers determine the proper speed and direction of an aircraft by taking into account the velocity of the wind, path of the aircraft, and local air traffic. They use radar equipment as well as their view from the control tower to follow the motion of all aircraft flying near the airport. 5.2 Velocity vectors. The vector in figure 5.1 is scaled so that 1 centimeter represents 20 kilometers per hour. It is 3 centimeters long and points to the right. Therefore, it represents a velocity of 60 kilometers per hour to the right, or 80 kilometers per hour east. It is really not, that the picture is not scaled, but it gets the idea across. The velocity of something is often the result of combining 2 or more velocities. For example, an airplane's velocity is a combination of the velocity of the airplane relative to the air and the velocity of the air relative to the ground, or the wind velocity. Consider a small airplane slowly flying at 80 kilometers per hour relative to the surrounding air. Here's figure 5.1. This vector scaled so that 1 centimeter equals 20 kilometers per hour, represents 60 kilometers per hour to the right. Well, it's not 3 centimeters, but fair enough. You get the idea. Suppose there is a tailwind blowing north at a velocity of 20 kilometers per hour. This example is represented with vectors in figure 5.2. Here the velocity vectors are scaled so that 1 centimeter represents 20 kilometers per hour. Thus, the 80 kilometers per hour velocity of the airplane is shown by a 4 centimeter vector, and the 20 kilometers per hour tailwind is shown by a 1 centimeter vector. With or without vectors, we can see that the resulting velocity is going to be 100 kilometers per hour. Without the tailwind, the airplane travels 80 kilometers in 1 hour relative to the ground below. With the tailwind, it travels 100 kilometers in 1 hour relative to the ground below. Now suppose the airplane makes a U-turn and flies into the wind. Figure 5.2. The airplane's velocity relative to the ground depends on the airplane's velocity relative to the air and on the wind's velocity. Consider this figure very carefully. It will help you with the early calculations. The velocity vectors are now in opposite directions. The resulting speed of the airplane is 80 minus 20, which equals 60 kilometers per hour. Flying against a 20 kilometer per hour wind, the airplane travels only 60 kilometers in 1 hour relative to the ground. We didn't have to use vectors to answer questions about tailwinds and headwinds, but we'll now see that vectors are useful for combining velocities that are not parallel. Consider an 80 kilometer per hour airplane flying north caught in a strong crosswind of 60 kilometers per hour, blowing from west to east. Figure 5.3 shows vectors for the airplane velocity and wind velocity. The scale is 1 centimeter equals 20 kilometers per hour. The sum of these two vectors, called the resultant, is the diagonal of the rectangle described by the two vectors. The resultant of two perpendicular vectors is the diagonal of the rectangular constructed with the two vectors as sides. We learned this in Chapter 2. Here, the diagonal of the constructed rectangle measures 5 centimeters, which represents 100 kilometers per hour. And here is figure 5.3, an 80 kilometer per hour airplane flying in a 60 kilometer per hour crosswind has a resultant speed of 100 kilometers per hour relative to the ground. So relative to the ground, the airplane moves 100 kilometers per hour northeasterly. In figure 5.4, we see a 3-unit vector at right angles to a 4-unit vector. Can you see that they make up the sides of a rectangle, and when added vectorially, they produce a resultant of a magnitude of 5. Note that 5 squared equals 3 squared plus 4 squared. In the special case of adding a pair of equal magnitude vectors that are at right angles to each other, we construct a square, as in figure 5.5. For any square, the length of its diagonal is root 2, or 1.414, times either of its sides. Thus, the resultant is root 2 times either of the vectors. 5.4, the 3-unit and 4-unit vectors add to produce a resultant vector of 5 units at 37 degrees from the horizontal. Five point three, components of vectors. Often we will need to change a single vector into an equivalent set of two component vectors at right angles to each other. Any vector can be resolved into two component vectors at right angles to each other, as shown in figure 5.6. Two vectors are at right angles that add up to a given vector are known as components of the given vector they replace. The process of determining the components of a vector is called resultant. Any vector drawn on a piece of paper can be resolved into vertical and horizontal components of that particular vector, and the resolution is called the resultant. Figure 5.6, a ball's velocity can be resolved into horizontal and vertical components. The perpendicular components of a vector are independent of each other. Vector resolution is illustrated in figure 5.7. Vector v represents a vector quantity. First, vertical and horizontal lines are drawn from the tail of the vector top. Second, a rectangle is drawn that encloses the vector v as its diagonal bottom. The sides of this rectangle are the desired components, vectors x and y. How do components of a vector affect each other. All right, here is vector v, and vector x and y are components of vector v. Vector v is actually the resultant. If I was given x and y, I would find the resultant v, but now I'm just simply going to work backwards and find the components for vector v. 5.4, projectile motion. A cannonball shot from a cannon, a stone thrown into the air, a ball rolling off the edge of a table, a spacecraft circling Earth. All of these are examples of projectiles. A projectile is any object that moves through the air or space acted on only by gravity and air resistance, if any. Projectiles near the surface of Earth follow a curved path that at first seems rather complicated. However, these paths are surprisingly simple when we look at the horizontal and vertical components of the motion separately. The horizontal component of motion for a projectile is just like the horizontal motion of a ball rolling freely along a level surface without friction. When friction is negligible, a rolling ball moves at a constant velocity. The ball covers equal distances in equal intervals of time, as shown in figure 5.8a. With no horizontal force acting on the ball, there is no horizontal acceleration. Figure 5.8a and b. Projectile motion can be separated into components. A. Rolling a ball along a horizontal surface and its velocity is constant because no component of gravitational force acts horizontally. B. Drop it and it accelerates downward and covers a greater vertical distance each second. The same is true for the projectile with no horizontal force acts on the projectile. The horizontal component of the velocity remains constant. The vertical component of a projectile's velocity is like the motion of a freely falling object. Gravity acts vertically downward, like a ball dropped in midair. A projectile accelerates downward, as shown on the right in figure 5.8b. Its vertical component of velocity changes with time. The increasing speed in the vertical direction causes a greater distance to be covered in each successive equal time interval. Or if the ball is projected upward, the vertical distance of the travel decreases with time on the way up. Most important, the horizontal component of motion for a projectile is completely independent of the vertical component of motion. Each component is independent of the other. Their combined effects produce the variety of curved paths that projectiles follow. Concept check. Describe the components of projectile motion. Notice that in equal times, both balls fall the same vertical distance. Gravity acts only downward, so the only acceleration of the ball is downward. The second thing to note is that both balls fall the same vertical distance in the same time. The vertical distance fallen has nothing to do with the horizontal components of motion. The downward motion of a horizontally launched projectile is the same as that of free fall. The path traced by a projectile accelerating only in a vertical direction while moving at a constant horizontal velocity is a parabola. When air resistance is small enough to neglect, usually for slow moving or very heavy objects, the curved paths are parabolic. Toss a stone from a cliff and its path curves as it accelerates toward the ground below. Figure 5.10a shows how the trajectory is a combination of constant horizontal motion and accelerated vertical motion. Concept check. Describe the downward motion of a horizontally launched projectile. Figure 5.10. No matter the angle at which a projectile is launched, the vertical distance of fall beneath the idealized straight line path is the same for equal times. Here's A, B, and C. A. The trajectory of a stone combines horizontal motion with the pull of gravity. B. The trajectory of the stone combines the upward motion with the pull of gravity. And C. The trajectory of the stone combines downward motion with the pull of gravity. Study this figure 5.10 carefully. Think, at the instant a horizontally pointed cannon is fired, a cannonball held at the cannon side is released and drops to the ground. Which cannonball strikes the ground first? The one fired from the cannon or the one dropped? All right, here is 5.9 to remind you that the two horizontal and vertical vectors are independent. Both cannonballs fall the same vertical distance with the same accelerating g and therefore strike the ground at the same time. Do you see that this is consistent with our analysis of figure 5.9? Ask which cannonball strikes the ground first when the cannon is pointed at an upward angle. In this case, the cannonball that is simply dropped hits the ground first. Now consider the case when the cannon is pointed downward. The fired cannonball hits first. So upward, the dropped cannonball hits first. Downward, the fired cannonball hits first. There must be some angle where both hit the ground at the same time. Do you see? It would be when the cannon is dropped neither upward nor downward, that is, when it is pointing horizontally. 5.6, projectiles launched at an angle. In figure 5.10, we see the paths of stones thrown horizontally and at angles upward and downward. The dashed straight lines show the ideal trajectories of the stones if there were no gravity. Notice that the vertical distance that the stone falls beneath the idealized straight line path is the same for equal times. This vertical distance is independent of what's happening horizontally. Figure 5.11 shows specific vertical distances for a cannonball shot at an upward angle. If there were no gravity, the cannonball would follow the straight line path shown by the dashed lines. But there is gravity, so this does not occur. So let's look again at 5.10 And then let's look at 5:11. So here's a perusal. We'll look at 5:10, A, B, and C, horizontal, pointed upward, and then pointed downward. And then at 5:11, with no gravity, the projectile would follow the straight line path, dashed line, but because of gravity, it falls beneath this line, the same vertical distance it would fall if it were released from rest. Compare the distances fallen with those in table 4.3. Okay, what happens is that the cannonball continuously falls beneath the imaginary line until it finally strikes the ground. The vertical distance it falls beneath any point on the dashed line is the same vertical distance it would fall if it were dropped from rest and had been falling for the same amount of time. Note, the longest time a jumper is airborne for a standing jump, hang time is 1 second, for a record of 1.25 meters, 4 feet height. Can anyone in your school jump that high, raising their center of gravity 1.25 meters above the ground? Not very likely. This distance introduced in Chapter 4 is given by d equals 1/2 gt squared, where t is the elapsed time. Using the value of 10 meters per second squared for g in the equation yields d equals 5t squared meters. Height. We can put this another way. Toss a projectile skyward at some angle and pretend there is no gravity. After so many seconds t, it should be at a certain point along a straight line path. But due to gravity, it isn't. Where is it? The answer is it's directly below that point. How far below? The answer is 5t squared meters below that point. How about that? The vertical distance a projectile falls below an imaginary straight line path increases continually with time and is equal to 5t squared meters. Note also from figure 5.11 that since there is no horizontal acceleration, the cannonball moves equal horizontal distances in equal time intervals. That's because there is no horizontal acceleration. The only acceleration is vertical in the direction of Earth's gravity. Figure 5.12 shows vectors representing both the horizontal and vertical components of velocity for a projectile on a parabolic path. Notice that the horizontal component is always the same and that only the vertical component changes. Note also that the actual resultant velocity vector is represented by the diagonal of the rectangle formed by the vector components. Here is another shot of 5.11 with the table 4.3 in the upper left-hand corner for your perusal. And then figure 5.12, the velocity of a projectile is shown at various points along its path. Notice that the vertical component changes while the horizontal component does not. Air resistance is neglected. At the top of the path, the vertical component shrinks to 0, so the velocity there is the same as the horizontal component of the velocity at all other points. Everywhere else, the magnitude of velocity is greater, just as the diagonal of a rectangle is greater than either of its sides. Range. Figure 5.13 shows the path traced by a projectile with the same launching speed, but at a steeper angle. Notice that the initial velocity vector has a greater vertical component than when the projection angle is less. This greater component results in a higher path. However, since the horizontal component is less, the range is less. Here is figure 5.13, the path for a projectile fired at a steep angle. Again, air resistance is neglected. Okay, let's look at horizontal ranges. Figure 5.14 shows the path of several projectiles, all having the same initial speed but different projection angles. The figure neglects the effects of air resistance, so the paths are all parabolic. Notice that these projectiles reach different heights, altitude above the ground. They also travel different horizontal distances, that is, they have different horizontal ranges. The remarkable thing to note from figure 5.14 is that the same range is obtained for two different projection angles, angles that add up to 90 degrees. For example, an object thrown into the air at an angle of 60 degrees will have the same range as if it were thrown 30 degrees with the same speed. Let's look at this figure now. The paths of projectiles launched at the same speed but at different angles. The paths neglect air resistance. Of course, for the smaller angles, the object remains in the air for a shorter time. Maximum range is usually attained at an angle of 45 degrees for a thrown javelin, and the other hand, maximum range is achieved for an angle quite a bit less than 45 degrees because the force of gravity on the relatively light javelin is significant during launch, just as you can't throw a heavy rock as fast upward as sideways. So it is that the javelin's launch speed is reduced when thrown upward. Speed. We have emphasized the special case of projectile motion for negligible air resistance. Figure 5.15, maximum range is attained when the ball is batted at an angle of nearly 45 degrees. As we can see in figure 5.16, when the effect of air resistance is significant, the range of the projectile is diminished and the path is not a true parabola. If air resistance is negligible, a projectile will rise to its maximum height in the same time it takes to fall from that height to the ground. This is due to the constant effect of gravity. The deceleration due to gravity going up is the same as the acceleration due to gravity coming down. The speed it loses going up is therefore the same as the speed it gains coming down, as shown in figure 5.17. So the projectile hits the ground with the same speed it had originally when it was projected upward from the ground. For a short-range projectile motion, such as a batted ball in a baseball game, we usually assume the ground is flat. In the presence of air resistance, the path of the high-speed projectile falls below the idealized parabola and follows the solid curve. And it can be significant depending upon the conditions. Figure 5.17, without air resistance, the speed lost while the cannonball is going up equals the speed gained while it is coming down. The time to go up equals the time to come down. However, for very long-range projectiles, the curvature of the Earth's surface must be taken into account. We'll see that if an object is projected fast enough, it will fall all the way around the Earth and become an Earth satellite. More about satellites in Chapter 14. Describe how far below an imaginary straight line path a projectile falls. Think. A projectile is launched at an angle into the air. Neglecting air resistance, what is the vertical acceleration? It's horizontal acceleration. A point to ponder. Its vertical acceleration is g because the force of gravity is downward. Its horizontal acceleration is 0 because no horizontal force acts on it. Think, at what point in its path does a projectile have minimum speed? Well, the horizontal forces are constant. The horizontal forces are constant. The minimum speed of a projectile occurs at the top of its path. If it is launched vertically, its speed at the top is 0. If it is projected at an angle, the vertical component of velocity is still 0 at the top, leaving only the horizontal component. So the speed at the top is equal to the horizontal component of the projectile's velocity at any point. How about that? Which coin hits the ground first? Place a coin on the edge of the table so that it hangs over slightly. Place a second coin on the table some distance from the first coin. Slide the second coin so it hits the first and both coins fall to the floor. Which coin hits the ground first? Think. Does your answer depend on the speed of the coin? Explain. How can you model projectile motion? 1. Mark a ruler at 5 equal spaces. From the first mark, hang a bead on a 1 centimeter long string. At the next mark, hang a bead on a 4 centimeter long string. 2. Hang beads at the next 3 marks with strings of length 9, 16, and 25. Hold the ruler at different angles and see where the beads hang. Think. Why is this model accurate? Hang time revisited. Recall our discussion of hang time in Chapter 4. We stated that the time one is airborne during a jump is independent of horizontal speed. Now we see why this is so. Horizontal and vertical components of motion are independent of one another. The rules of projectile motion applying to jumping. Once the feet are off the ground, if we neglect air resistance, the only force acting on the jumper is gravity. Hang time depends only on the vertical component of liftoff velocity. It turns out that jumping force can be somewhat increased by the action of running, so hang time for a running jump usually exceeds that of a standing jump. However, once the feet are off the ground, only the vertical component of liftoff velocity determines hang time. Summary: projectile motion. A vector quantity includes both magnitude and direction, but a scalar quantity includes only magnitude. The resultant of two perpendicular vectors is the diagonal of the rectangle constructed with the two vectors as sides. The perpendicular components of a vector are independent of each other. The horizontal component of motion for a projectile is just like the horizontal motion of a ball rolling freely along a level surface without friction. The vertical component of a projectile's velocity is like the motion for a freely falling object. The downward motion of a horizontally launched projectile is the same as that of free fall. The vertical distance a projectile falls below an imaginary straight line path increases continually with time and is equal to 5t² meters.